We will now take a look at first-order reactions involving drug degradation. Again, these principles will be the same as drug elimination from the body when we get to pharmacokinetics. So in first-order reactions, the amount of drug that's lost is dependent upon the amount of drug that is present. And specifically, the amount of drug that is lost will decrease as the amount of drug that's present decreases. So they'll follow the same trend. Therefore, the fraction of drug that is lost over time will remain constant. And in this case, a plot of the natural log of drug, either drug amount or drug concentration versus time, will be linear. We can look at an example of a drug that undergoes first-order elimination. Again, the time interval that we're looking at here is constant, so those are 1 hour time intervals. If you look at the second column, notice that the amount of drug that's in the body that we're eliminating for each interval changes. So in the first hour, we lose 120 milligrams of drug. Over the second interval, we lost 106 milligrams of drug. And you can see that that amount decreases, the amount that we're losing decreases as the amount of drug in the body that was present decreases. Also notice if you look at the column on the far right, this means that the fraction of drug that we're eliminating each hour is the same. So that's why the amount is changing. And so here our elimination rate constant, or our first order rate constant for elimination, K, is going to be equal to the 0.12 per hour. We derive these fractions by taking the amount eliminated over the amount that's total that's present. So 120 milligrams was lost in the first hour out of 1,000 milligrams that was present. That's equal to 0.12 as a fraction. We then lose 106 milligrams out of 880 milligrams that were present. Again, that's going to be a fraction of 0.12, so that is constant. If we now take a look graphically at a first order process, with these first order processes, we are plotting the natural log of the drug amount or drug concentration versus time. This is going to be linear and is described by that equation, y equals 6.9078 minus the 0.128x. So recall our linear equation is y equals mx plus b. So in this case, our y is the natural log concentration, is equal to the slope, which is our negative rate constant k, times x, which is our time, plus the y-intercept, which is ln of our initial concentration. And so oftentimes this is just rearranged, where we write lnc is equal to lnc0 minus kt. When solving for drug concentration at any time, it's sometimes easier to manipulate this equation by basically taking the antinatural log of each side, which would have this equation reduced down to c equals c0 times e to the negative kt. So those are the same. It just depends on what you're solving for as to which form of the equation is easier to work with. Alright, so if we now take that equation, the LNC equals LNC0 minus KT, we can derive our equations for half-life and shelf life for drugs that decay by a first-order process. What I've done is in the top corner here, I've just rearranged the equations so that we're solving for our time t. So if we manipulate that equation, our time is going to be equal to ln c over c0. and that whole thing is going to be divided by the negative K. So for our half-life, what we're looking to do is solve for that time when our concentration is at 50%. So at this time, our C is going to be equal to 0.5 times C0. So we're now going to substitute that into that the above equation. So our T is going to be equal to ln of 0.5 C0 over C0. Essentially, we're just taking the natural log of 0.5, and that's over negative K. And so we're going to see that our half-life then for a first order process is going to be equal to 0.693 over K. A lot of people just find it easier to memorize this equation since it's one you'll use a lot. But if you forget, you can always derive it by plugging in that arbitrary concentration of 0.5 C0 in for C and then solving the equation. We can take a similar approach to looking at shelf life. So recall our shelf life is when our concentration is going to be equal to 90% of the original concentration. So we can plug that term into our equation, and we would find that our time would be equal to ln 0.9 times C0 divided by C0. So essentially we're just taking the natural log of 0.9 over negative K. So ultimately our T90 then is going to be equal to 0.105 over K. So that's the shortcut equation that we've been using. So once again, you can either memorize these shortcut equations to save you a little bit of time, but if you forget, you can always just solve for them using these concentrations. Either C equals 0.5 C0 or C would be equal to 0.9 C0. And that wraps it up for our first order reactions.